Now we're going to take a closer look at equivalence relations. So we're first going to review the definition of equivalence relations, and we're going to show how to prove that a given relation is an equivalence relation. So here are the properties that make up the definition of equivalence relations. Let A be a set and let R be a relation on the set A. We say that the relation R is reflexive if every element is related to itself. So A is related to A for every element A in the set big A. We say that R is symmetric if whenever A is related to B, then B is related to A. And we say that R is transitive if whenever A is related to B and B is related to C, then we conclude that A is related to C. And this leads to the definition of equivalence relations. If, again, let A be a set and let R be a relation on A, then R is an equivalence relation if it satisfies the reflexive property, the symmetric property, and the transitive property. And before we head to the next slide, I want to go back to some of the definitions of reflexive, symmetric, and transitive. The last two are pretty clear in terms of being if-then statements. It's very clear what you assume. So for symmetric, you assume A is related to B, then you try to prove that B is related to A if you're trying to prove something is symmetric. And transitive, what you assume is A is related to B and B is related to C, then you want to prove A is related to C. And what you might notice with the reflexive property, it's not completely clear what you're assuming, what you're trying to show. So I will address that when we actually try to prove it for a given relation, but just realize that it's really important when you're trying to prove something, you need to know what you're assuming and what you're trying to show, and sometimes it may not be obvious from the statement of the definition. Anyway, so on to the next one. So now we're going to go ahead and define an example relation, and then we're going to prove it's an equivalence relation. So we're going to call our relation E, because we anticipate it's going to be an equivalence relation, and it's going to be defined on the real numbers. And so here's the definition. We're going to define that x is related to y when x squared is equal to y squared. So we take two real numbers, we square them. If their squares are equal, they're related. If their squares are not equal, then they're not related. All right, let's start with the reflexive property. And this is a tough one because it's not obvious what it is that we're trying to assume. It is pretty obvious what we're trying to show, right? We take an element, some kind of element in the set and prove that it's related to itself. But what are we assuming about that element? Well, it turns out all we're assuming about our element, I'll call it x, is that it is in the real numbers, right? Our relation is defined on the real numbers, so we're assuming our element x is in the real numbers. So we are assuming something. It seems pretty obvious, but it's important to say because we have to be clear about what we're assuming. So we're going to assume that x is in R, and we're going to show that x is related to itself. X is related to x. So remember, the test for x being related to y is seeing whether or not x squared is equal to y squared. And so if we replace that y with an x, which is what we're doing when we're asking is x related to x, the test for x related to x is it true that x squared is equal to x squared? And it certainly is. X squared is equal to x squared because they're exactly the same thing. That means that it follows that x is related to x. All right, so the other ones are have a better flow to them. So now the next one is the symmetric property. We're going to assume that x is related to y, and we're going to show that y is related to x. That's how the symmetric property works. So x is related to y, that means that x squared is equal to y squared. Now the way equality works, it works in either direction. That implies that y squared is equal to x squared, but that is exactly the test for y being related to x. So we can conclude that y is related to x. And finally, with the transitive property, we're going to assume that x is related to y, we're going to assume that y is related to z, and then we're going to show that x is related to z. Now, we know that x is related to y, that means, and we know that y is related to z, right? So that means x squared is equal to y squared, since x is related to y, and y squared equals z squared, that's because y is related to z. Now, x squared and z squared are both equal to that same y squared, which means that they're equal to each other. So we know then that x squared is equal to z squared, but that is exactly what it means for x to be related to z, so it follows that x, e, z. So that means that E satisfies the reflexive property, it satisfies the symmetric property, and it satisfies the transitive property. And that means that E is an equivalence relation. All right, so now I think you're ready to work on the activities for equivalence relations, and that's the PDF file included with this video.